Okay, today we're going to talk about gas laws. In order to be successful in this unit, you need to remember some things about gases themselves. We talked about how gases have no set shape and no set volume. Gases are fast-moving molecules that will occasionally collide with each other. Remember, I told you the way to remember a gas is to think of some 2-year-olds that are running on the playground. They play independently of each other, and then occasionally you'll have a collision. When the kid coming down the slide collides with the kid throwing the rocks up the slide, you're going to have a collision. Temperature and pressure are able to change the volume of a gas. We saw that in our introductory lab with this unit. Now, the reason temperature and pressure was able to change the volume is because those molecules have a lot of empty space around them, so they can move around. When they get more temperature added to them, they can spread out even more, and they will continue to spread out as you add temperature until they hit the boundary of whatever's containing them. And then that boundary will apply pressure, which holds the volume in. Now, standard temperature and pressure is a common phrase that you will hear in the problems that we'll be doing in class. Standard temperature is 0 degrees Celsius or 273 Kelvin. Now, remember that Celsius is based on water's properties. So it's convenient to remember that 0 degrees Celsius is freezing, 100 degrees Celsius is boiling. But when I put 0 into an equation, some interesting things happen that we know can't really happen. Mass cannot be created or destroyed. And if I put 0 into an equation and multiply it with a number, I'm going to get an answer that says that 0 happened. And I can't have 0 grams or 0 milliliters of a substance. So we have this Kelvin system that is based on absolute 0. Every time you see Celsius in a problem, make sure that you change it to Kelvin by adding 273. And if a problem asks you for what the resulting temperature is in Celsius, you simply take your Kelvin answer, subtract 273 from it to get the Celsius. Now, standard pressure has two different units. We have 760 millimeters mercury and we have 1 atmosphere. The reason we have two different values is because we use pressure for multiple things. We talk about millimeters of mercury when we're talking about barometric pressure, like when you watch the weather station and they talk about high pressure system or low pressure system. They're talking about the barometric pressure. Atmospheres is your atmospheric pressure. When you go to fly on an airplane from the East Coast to the West Coast, or if you go transcontinental, you will have to go at a very high elevation in the airplane and you'll experience some pressure in your ears. That's because you are at a low atmospheric pressure on the outside of your ear, and inside your ear you have standard pressure, and you start feeling like you need to pop your ears. Well, when you do that, what you're doing is equalizing the pressure. If you go deep sea diving, you get into conditions of high pressure, and you have to come up slowly for the same reason. Alright, so now we're going to start talking about the different gas laws that we will be dealing with in class. And the first one is Charles's Law. Charles's Law states that as the temperature of a gas increases, the volume of the gas also increases. Now, this is a direct relationship because as one goes up, so does the other. We have our formula then, T1 over V1. This is where the gas starts. And if one goes up, the other will also go up the same rate. So we set them equal to each other as a ratio. Now, most of you don't like fractions, so I've rewritten the formula as T1V2 equals T2V1. It's the same formula as what we have here. It's just that I have rearranged it so that you don't have a fraction to deal with in the beginning. Now, Boyle's Law is the law dealing with pressure. And one way that I remember this is when you want to boil something for long periods of time, but you don't want all the water to boil out, you'll use a pressure cooker. Well, boil and pressure then go together. Boyle's Law states that as the pressure of a gas increases, the volume of the gas decreases. That's an inverse relationship. So we write it here is P1V1 when we start, but as one goes up, the other has to go down, so we write it across the relationship, across the equation for you. No fractions to rearrange, so we just have the one equation to remember. Now this theory or law, Galois Law, I want you to be familiar with, but we're not going to do a lot of problems with it. The reason we need to learn it is because it connects Charles's Law and Boyle's Law, which talked about pressure and temperature separately. This law connects them together. And that's important because it opens up the doorway for the other laws that we'll be talking about in a moment. So Galois Law states that when the volume and mass of a substance are constant, in other words, it doesn't change, then we know that an increase in one temperature would cause an increase in the pressure. So if I keep the volume the same and I increase the temperature of that gas, it's going to want to expand. And the pressure then will have to increase to hold the volume in. So if I want to keep the volume constant, then an increase in temperature will cause an increase in pressure. The combined gas law states that there is a ratio between the pressure-volume product and the temperature of a system. If one thing remains constant, if two things remain constant, then the other thing will change. So we're going to have P1V1 over T1. Now, if I say that the volume remains constant and I change the pressure, then I can find out what the new temperature will be. If I keep the temperatures constant and I change the volume, I can find out what the new pressure will be. So we will keep one thing constant, we will change a second thing, and the third thing is what we will solve for. The formula without fractions says P1V1 T2 equals P2V2 T1. Make sure you keep the ones and the twos in the right place. Okay, and that leads us to our last gas law, which is the ideal gas law. The ideal gas law has a lot of things that have to be true before you can say a gas is an ideal gas. I like to think of it as a perfect gas. So these are the things that have to be true for a gas to be perfect. It must obey all the gas laws, and it cannot condense as it cools. And it must always show a straight line graph, which means it's constant for VT graphs and PT graphs, pressure, temperature, volume, temperature graphs. Now, the reality is that no gas is perfect. Just like people aren't perfect, gases aren't either. But in order for us to look at the molar relationship from one gas to another, we pretend that these gases are perfect under certain conditions. And we use this formula to relate everything together. PV equals nRT. Now, we've seen the P, the V, and the T before. The two things that are new are the N and the R. N means moles. It's the number of moles of the gas. And R is the constant that makes this equation true. If I took this out, this would be an untrue equation. So what this constant is telling me is that I need a constant value of 8.81 to multiply right here in order to make this relationship true for every ideal gas. Now, this 8.81 is a derived constant with a derived unit of kilopascals times liters divided by Kelvin times moles. Now, the only reason we have all those units in there is so that when we put it in here to our equation, all of our units will cancel except for the one we're looking for. So if I have moles and I have temperature and I have volume, then the liters, the kelvins, and the moles will cancel, leaving me with the kilopascals, which is the pressure unit.